All right, thanks everyone. So our presentation today is by Robin Morisset. He was an intern with us in the native client group at Google. He did a lot of work on atomics for C11 within LLVM. He's a PhD student at INS Paris, and so he'll be going back to finish his PhD after this week. So with that, Robin.
Thank you. Can you hear me? So I will focus on optimizations done in LLVM for C11 atomics, but I will start by some quick explanation of what atomics are. So the main question is what can happen to your code when it is running on several cores at the same time. So for example, if you look at this code, you may think that it can never print 0, 0, because if you look at all the possible interleavings of the different actions, there is no way that you can have each print before the corresponding store. But first, you can have the compiler that can decide to schedule the operations in another order. Even worse, you can have the processor decide to send the stores not directly to memory, but to a store buffer. And so you must add some special instruction called a fence, telling the processor, don't do that. Make sure that you send the store of x equal 1 to everyone and before you do the load of y, and symmetrically on the other side. So what about this code? This may seem fine, because even if the store is delayed on x86, the store buffer is first in, first out. So by the time ready equal 1 is visible, x equal 42 will also be visible. However, on ARM, the store buffer is not first in, first out. So you could have the two stores reordered by the processor, so you need another kind of fence for telling it, don't do that. And actually, it is even worse, because the processor could decide to speculate the load of x on the other hand, on the other core, before loading ready and doing the branch. So you must add another fence, which happens to be exactly the same instruction. So at this point, it appears to be pretty tricky to write a log-free code, because for every processor, you need to know exactly what kinds of optimizations it can do to your code and to prevent them by some careful fences. So ideally, that is why we have programming languages to abstract from that. So C11 and C11 introduced atomics and a memory model for letting the programmer write portable concurrent code. So there are three big ideas. The first one is that if your code have races and no special atomics, then it is garbage, and the compiler is allowed to do anything it wants. The second one is that if your code is well locked, so you are using mutatexes, for example, for synchronization, then everything works fine as it always had. So you can reason just based on the interleavings of actions without having to know anything about atomics or about fences. However, because C and C++ are for lower level high performance code, you may want to write log-free code. And so you can tag every load and store that you know is racy with an attribute for telling the compiler, I know this code is racy, and I want you to introduce fences to guarantee this or that. So the strongest attribute you can put is sexCST, meaning sequentially consistent. This means I want only the behaviors that can be had by interleavings of actions. So make sure that there is no weird reordering going on either at the processor level or at the compiler level. But as we saw, that is too much, because this requires fancies on x86. And in this example, we only require fancies on ARM. So for performance, you may want to say, I'm fine with something cheaper. You may say, I'm fine with release on store and acquire on load. So the semantics of those is that if a release store is read by a load acquire, then everything that was before that store will be visible to everything after that read. And so the compiler is free to do anything it wants as long as it guarantees this. So in particular, it means that things after the release can be hoisted before it, but things before the release cannot be sent below it. So it acts as a one-way barrier, actually. The right way of thinking about those is that the acquire behaves as the beginning of a critical section, and the release acts as the end of a critical section. So now the obvious question is, what about all our old optimizations? Are they still correct in this new world? Turns out that you must be somewhat careful, because, for example, here you have some code that is modifying x in a loop, and you want to do a loop invariant code motion to only update that x at the end of the loop. And if you do it like this, in the obvious way, then when n is equal to 0, you've just introduced save and restore of x, which may still seem fine. But if you have another thread messing with x, you have just introduced a race and possibly changed the behavior of that other thread. So a first rule for optimizations in a world with atomics is that you should not introduce stores when there could have been none. So this optimization is fine as long as you check that n is different from 0. Another example that may seem simpler is what happens if you try to eliminate an access. For example, what happens if you try to eliminate a dead store? The old rule was that you have no access that is aliasing x in between. But it is not enough, because you could have this code in between and have another thread running this. And so this other thread is loading x and printing it. So if you eliminate the store of 42 into x, then it can now see garbage. So you would have changed the behavior. And the release and acquire here are really important, because they are what let you pass control to the other thread safely without having races. In particular, if you only had an acquire, then you are fine, because any thread that read x would be racing with your store to x, and so would be undefined behavior. Similarly, if you only had a release, then it would be racing with your second store, and you would also be fine. So the general rule for all kinds of elimination, so here the example is dead store elimination, but it also applies to lots of other things, is that you must be careful when you have a release followed by an acquire, because this is the pattern that lets you hand off control to another thread and then take it back safely. And so anything can happen whenever you see a release followed by an acquire, because arbitrary code can be running. So this was about optimizations around atomics, but one of these questions is can you optimize the fancies themselves? And actually, yes, you have lots of opportunities, because by default, a compiler just see, OK, this is an acquire, so I am on ARM, so I must add a fence just after it, and this is a release, so I must add a fence just before it. And then you can have two fences in a row, which is fairly useless because fences only order whatever is before them with whatever is after them. So having 1 or 17 is exactly the same. So you would like to find these patterns and eliminate one fence. What gets more tricky is what happens if you have control flow. So for example, here, you cannot eliminate any of the two fences, or you are breaking the synchronization with the other store. But you could move them in that way or in that way. And then you still have all the same synchronization that you had before, but you only have one fence on the main path. And so when looking at this and trying to find how to do it, I found that it is really close to the issue of partial redundancy elimination, in which the compiler is trying to make sure that a computation occurs at least once on every pass between the definition of its operand and the use of its result, and yet to minimize the cost. And what we are doing is exactly the same. We want to make sure that we have a fence on at least one fence on every pass between something that was before a fence and something that was after, and yet to minimize the cost. So I reused an algorithm which is based on min-cut. So the general idea is that you build a graph with one node before and after every access, with one node at every point where the control flow splits, and one node at every point where the control flow joins. Then for each fence, in turn, you take the first access before it, you add it to the source, and each access after it, you add it to the sinks. You do the same for the other fence. Then you put the cost of putting a fence on an edge to every edge. So here we use the int max for some of the edges just because we don't want, for some reason, to put a fence here. For example, if they are between blocks, because splitting edges is tricky. And for the cost, we are just using either profiling information or some heuristic. And then you do a min-cut. So you try to find the cheapest set of edges that completely separate the source from the sink. And actually, if you just put the fences on these edges, you can easily show that you still have exactly the same guarantees that you had before, and that you minimize the dynamic cost of the fences. So it may seem a bit too much, but, well, too much work for just this. But it is really useful for more tricky control flow, and it has a nice property that that it is very flexible. One example, for example, of a way you can reuse that is if you have a spin loop where you are repeatedly doing an acquire load. So you have a fence in the middle of the loop. It could be argued that the fence really should be after the loop, because you only want to synchronize with whatever is after the loop. Between one iteration of the loop and the other, you only have access to flag, and accesses to the same location are already ordered by the processor. And so it is not obvious if this wins a performance, but it might, and it is quite easy to do. All you need to do is to just say, when gathering the set of nodes that you connect to the sink, you should skip any node which is the node that introduced the fence in the first place. And this is enough to automatically sync the fence in that case. And there are other examples that I can talk about on how you can adapt this algorithm to all kinds of heuristics. So these were the interesting optimization where you try to be clever, but when I looked at what Clang was actually producing for atomics, I also found all sorts of small or not so small inefficiencies in the code gen. So one funny example is that you don't have a load release in a C11. A release is always a store. And the issue is that you want a release to end critical sections. So if you have a sec lock, which is a kind of lock where basically the writer increments some counter, and the reader at the beginning of the critical section reads from that counter, then reads again at the end and checks that the value is the same. Then you very much want to have your last load be released to end the critical section and to make sure that what is in the critical section cannot be reordered past it. So one trick suggested by Hensbaum in a paper is to use a fetch and add of 0. And this works because it is kind of a store, so you can make it release, and it returns the older value, so it behaves exactly as a load. The issue is that it produces instructions that modify the cache line, and so the processor will take an exclusive access to the cache line, creating all kinds of contention issue. And so one way of optimizing it is finding this specific pattern and replacing it by a fence followed by a load. And so this can give you some arbitrary speed-ups on benchmarks of this specific pattern, because you are reducing contention dramatically, because you are only loading from a cache line and not storing to it on every core. Another simple example is that most processors have several kinds of fences. So for example, you have a heavyweight sink or DMB system-wide on ARM. And these are often too much. For example, they are enough to guarantee a sec CST, but for release acquire, you have lightweight sink and DMB-ish, which are much cheaper. So it was not always using the right one. But a funny thing is that for some processors like the Apple Swift, you can go even further, and they can guarantee you that there are some even cheaper fences like DMB-ish, which is enough for some specific case. And I think this is a good reason for using atomics, because you can't expect every log-free programmer to know every possible platform, including possibly some platforms that will be developed later, and to know that they can use this specific instruction on this specific processor, whereas the compiler can adapt and specialize in that way. Another even more funny example is this. So you are compiling a store, an atomic store of a single byte of the immediate 2 to X on power. And you get all of this code, which is first doing all kinds of shuffling and byte twiddling. Then you have a loop. And in each iteration of the loop, you do a load linked and store conditional. So it seems really wasteful. And actually what happened is that the power backend was saying, I don't know anything about atomics, so I cannot compile an atomic store. And so it was saying expand, and so every atomic store was expanded into a loop of compare and exchange. And then every compare and exchange was transformed into a loop of load linked and store conditional. And then before load linked and store conditional are only implemented for well-aligned words on power, you must have all of this shuffling to make sure that things are well aligned and so on. And all this is a bit wasteful because this code just works. Because actually here you have relaxed, which is an attribute which says I don't need any fence. All I want is just that my access is atomic. So I just want my access not to be tiered in several parts. and a single byte access is atomic on pretty much everything. So it's pretty much free. There are some similar issues on x86, but less extreme, so some extra register use. Once again, it was not for some deeper reason. It was just that atomic stores are special cased in the back end, and so all of the optimizations on normal stores were not firing. However, not all is perfect with atomics. So the first issue is that relaxed attribute, which means I know what I am doing. I know that my code is racy. So please don't consider it undefined and make sure that my accesses really are atomic, but don't put any fence. So this means that this code can print 1-1, because on some machines it can happen. The big issue is that the C++ standard defines the memory model in terms of traces of events, which means that this is exactly the same from its point of view. So because x equal y equal 1 and printing 1-1 is allowed, here you can get x equal y equal 1, whatever the value of x and y were beforehand. So you can have values that pop out of thin air, which is fairly scary, but why not? But you can have things even crazier. So here you have a causal loop where you are saying, well, first I will assume that y is 1. So I will store 1 into x. So the other thread will see 1 into x, will store 1 into y, and so I can check that my assumption was correct, which is obviously insane. No actual machine will ever do that, I hope. And even compilers won't actually do that, but it is allowed by the standard. This is a huge issue because it breaks pretty much every analysis you may want to write for C or C++ code. It breaks pretty much every theorem you may want. Because the funny thing here is that both pieces of code are dead. So you can have two parts of the code which are dead individually, and if you run them in parallel, suddenly they can become live. If you combine this with the previous example where you can have values that appear out of nowhere, you can even build an example where you have two threads running some code on two linked lists which are completely separate, and the two threads are not talking to each other in any way. But because values can pop out of thin air, each thread can get a value which is actually a pointer to the other list out of thin air, and then each thread can start messing with the other and thus confirm the fact that, yes, actually the two lists are linked, which is just insane. So one big issue is how can you explicitly allow this while forbidding this and this? So this is a semantics issue, not really an implementation one, but it is tricky. Another horrendous example is consume. So first, here's a reminder for what release acquire does. It makes sure that everything before release is visible to everything after acquire. Consume is a weaker kind of acquire that says everything before the release is visible to everything that, that depends on the value that was loaded by the consumer. So here, for example, because we are reusing T, the two accesses are ordered. But here, where it is another variable, there is no guarantee, so you don't get that green arrow. So the reason why this is really useful is because consume is free on most machines, including ARM and Power. So for acquire, you must have a fence, not for consume. So it seems fine and nice until you get an example like this. And here the question is, does the value that is loaded depend on T or not? And technically, it does. According to the standard, it does. But as soon as you run pretty much any kind of optimization pass in your compiler, it doesn't anymore. And so the processor will be free to reorder things and so on. So the current way this is fixed in LLVM is to just deal with consume exactly like acquire. So just saying everything I say consume, I add a big fence. And this works just fine. The big issue with this is that it is costly because you add a fence in a situation like this where they are not required. And this kind of patterns is extremely common, for example, in the Linux kernel. And so they explicitly said, we won't be using C11 atomics until this is fixed, until you find a way of guaranteeing that consume is actually free. And so the big question is, so you can't just say, I will disable optimization in this case. Because instead of being just on the next line to the consume, this expression could be in a function in another module, which is just called here. So you would have to disable every optimization everywhere, which is obviously not good either. So we would like, ideally, the programmer to help the compiler by telling, I really care about this dependency. I really care that you don't eliminate this. But apart from that, have fun. And exactly how to define both the semantics and the syntax for these extra annotations that the programmer would have to add is really tricky. And so there are lots of ideas and suggestions. One will hopefully be chosen for C++17, but until then, it's still pretty much an open issue. So in short, I hope that I convinced you that atomics are useful if you are writing a log-free code because they can make it portable. And additionally, that they can be nicely optimized by compilers, even if it is somewhat tricky. But there are still lots of open researcher questions about them and lots of issues. So if you want to work on them, there is lots of fun to be had. Thank you.
All right, any questions?
Hi, thank you for the talk. I'm understanding correctly that you're dealing with full memory barriers. You're removing excessive full memory barriers. I mean, the full barriers compared to read barriers and write barriers.
Oh, yeah. So the C11 standard is not defined in terms of read barrier or write barriers. These are from the Linux kernel or alpha, and they say that we order every store before with every store after, or every load before with every load after. Whereas here, we are ordering everything before an access, with that access, and so on. Does that answer your question?
So there are aspects of thread safety that go beyond memory operations. You know, for example, say you're doing a multi-threaded internet application that's handling transactions and so forth. Like there's a meta state to those transactions that go beyond simply like, what order in which you're accessing memory. So I'm wondering whether people are trying to develop building blocks that will apply to those levels of thread safety, or like?
So yes, but it is at a very different level. Atomics are not designed to be used by every programmer who is developing his internet application. They are designed to be really the primitive building blocks so that other people can build frameworks with logs or transactions or whatever. And then on top of that, you can have your application without having to think about all of these tricks. So it is a different level, and I don't know as much about it.
Yeah, great, thank you.
You're welcome.
Any more questions? All right, thanks.
Oh.
One more? Okay, one more.
Is most of the support for this in all the back-end stuff, or is there front-end IR stuff that has to be aware of atomics and all that?
Okay, so the front end pretty much just translates the C code to very similar IR. It just has to be careful because the LLVM IR doesn't accept some illegal types. So if, for example, you're trying to do this with X being 16 bytes, it will have to emit a function call instead. In the middle end, you have some special code that must be careful for, where is it? For this. You must have some code in memory dependency analysis that checks that you don't have a release followed by an acquire. After that, most of the atomic expansion is done in the IR, but very late. It is actually a path which backends can register, which is called atomic expand, which will automatically, which takes a bunch of callbacks from the target and will expand, for example, acquire and release to DMB-ish or whatever the target wants. And then at that point, you only have basically intrinsics, and the target just emits them.
So you talked about causal loops in one of your concluding slides. So the Java memory model has this very weird, not weird, but complicated way of preventing them. Yeah. So do you see how that can be implemented in LLVM, and LLVM can be made aware of?
So in short, in Java, it is really required to prevent any kind of forging for type safety.
Yeah.
The C++ community was hoping that they could get away with lesser complexity because they don't really care about safety. But about that kind of type safety. Actually, you can't really get away without complexity, but even in Java, you still have lots of issues with the Java memory model. And additionally, I don't think they have all of these different levels with release, acquire, relax, consume, and so on.
It's just release, stores, and acquire loads.
Yes, so it is not clear that we can just reuse the same kind of tricks, which are already scary.
Okay, that's reassuring.
Any more questions? All right, thanks.
Thank you.